So like we talked about yesterday, last chapter, the very last thing, because it was a limits chapter, the very last thing we did in the limits chapter was continuity, right? Is something continuous at a point, right? And we checked it using this, right? Using these, that's the way we checked it, right? The limits, we checked it by limits, okay? The limit as x approaches a value from the left is equal to the limit as x approaches a value from the right is equal to, if those two are equal, then there's a limit at that point, and then we checked the y value at that point, right? F of c is the y value, okay? If those are equal, it was continuous. We said that last chapter. The only difference with what we're doing today is that we're not checking for continuity, we're checking for differentiability. So what's differentiability? Does it have a derivative? Okay, does it have a derivative? Is it continuous? That was last chapter. Does it have a derivative at that point? So why would it not have a derivative? Well, a couple of reasons why. First of all, it's not continuous, right? There's a jump discontinuity, there's a hole, there's an asymptote, right? Those are reasons why there wouldn't be a derivative at a certain point. Sharp turns, right? We talked about the sharp turns. There's two kinds of sharp turns. Here's one example, here's the other example, right? What causes a sharp turn? When we quickly change, we quickly go from increasing to decreasing. So if we quickly change that from either decreasing to increasing or vice versa, okay? Those make corner or cusp points, right? So how do we check to see if that's happening? We check the derivative. We say the derivative, what is the derivative coming in versus going out? So like, for example, before 0, it had a negative derivative, right? How do I know it's negative derivative? How do I know the derivative of this line is negative? I heard it somewhere.
Reading it from left to right, it's going down.
Yep, it's going downhill, right? Downhill means negative derivative, right? The slope of the tangent line is negative. -1, -2, -1/2. I don't know what it is because there's no y values on there or x values, but yeah. But at 0, look what happens. It changes. Now it's increasing, which means a positive derivative, right? So is it differentiable greater than 1? Or sorry, greater than 0? X equals 0? Yeah. Is it differentiable less than x equals 0? Absolutely. But what happens at 0? What's the derivative at this point here? I don't know. Is it negative or positive? I don't know, right? If it was like this, that's different. There's a slow gradual change, right? There's a slow gradual change from increasing to decreasing, okay? If that's the case, then it does have a derivative. But if there's a sharp point there or here, it's not differentiable. So how do we check that? Right here. We check the derivative. What's the derivative coming from the left side? What's the derivative coming from the right side? If they're the same, it's differentiable. There's no corners. Okay? And then the last thing, there can't be any vertical tangent lines. If I have a tangent line that's vertical like this, it's not going to have a slope because it's undefined, right? If it's vertical tangent lines, vertical lines in general, all have undefined slopes. Okay? All right, so we did a couple examples. I think we left off at number 4. So let's look at number 4. Okay. So continuity and differentiability go together a lot. A lot of times they're going to say, check continuity and check differentiability. Okay, we've done continuity before. Differentiability, we've done in these notes. So they might say both, they might say one. It just depends on what the problem says. Okay, so determine the values of a and b that would result in f of x being differentiable. So that means it's differentiable everywhere. Where does the rule change? Where does f of x change when x equals what? Negative 5, right? When x equals negative 5, the rule changes, right? If it's less than negative 5, I'm going to, where's my highlighter? There we go. I'm going to use that guy. When it's negative 5 or more, I'm going to use that guy, right? So that's where it changes at negative 5. Okay? So what we're going to do is it has to be differentiable. It has to be differentiable because it says would result in being differentiable. So what I'm going to do is I'm going to figure out what A and B need to be for it to be differentiable. So differentiable at x equals negative 5. Okay, so again, to check for differentiability, I'm going to use derivatives. We use derivatives, not the original. If you're checking for continuity, we're going to use f of x, but we're checking for differentiability. So we need to check. So first thing we need is a derivative. Okay, so I'm going to take the derivative of f of x. It's a piecewise function, so it's got two pieces to it. So what is that going to look like? It's going to look like this. F prime of x. So the green, or sorry, not the green, the right below that, the orange. The orange is ax minus 6. Remember, a is a value. So what's the derivative of ax minus 6? Just a, right? Just a. X is the variable, a is a number. So if that said 2x, the derivative would be 2. If it said 4x, the derivative would be 4. Okay, so 4x is less than negative 5. Okay, and now we're going to do derivative of the magenta color there. So the magenta color, we would go move the 2 in the front, so it would be 4bx plus 3, right? For x is greater than or equal to negative 5. Okay, that's the derivative of f of x. Doesn't matter if it's piecewise or not, that's how you find the derivative. Okay, so now what we're going to do is we're going to check the derivative at negative 5 as x approaches negative 5 from the less than side. And then we're going to compare that with the derivative at negative 5 as x approaches negative 5 from the right. So that means we're going to plug in negative 5 to the derivative. Well, if I'm coming from the less than side, less than, I'm going to use the top guy. But there's nowhere to plug in negative 5 because there's no x, right? So it's just going to equal a. Then I'm going to do the same thing for the greater than side, 4bx plus 3. There I can plug in negative 5 for x. So we get 4b times negative 5 plus 3. So we're going to get negative 20b plus 3, and that equals a.
Let's see if the restrooms open now.
Yeah, go ahead.
Thank you.
Okay. So I have an equation, a linear equation. It says a equals negative 20b plus 3. When you have two variables you need to solve for, like if it was just one variable, I could solve for that variable, right? I could isolate a or I could isolate b, right? But if I have two variables, I can't isolate. It doesn't really help me. So what I need is another second equation, okay? So how am I going to build that? I'm going to use continuity this time. So I'm going to use continuity. Because if it's differentiable, it also has to be continuous. Okay? Because if it's differentiable, like it says it was, it also has to be continuous. So this one is what we did last chapter, the limit for f of x as x approaches negative 5 from the left, is equal to the limit as x approaches negative 5 from the right. That has to be equal to f of negative 5, the y value. Okay? So essentially you're going to do the same thing. Plug in negative 5 for x. But instead of using the derivative, you're going to use the original. So we're going to plug it in. So from the left, we use ax minus 6, the orange highlighted one. So a times negative 5 minus 6. So that's negative 5a minus 6. Now plug it into the bottom. 2b negative 5 squared plus 3 times negative 5 minus 5. So we get, what is that, 25 times 2, 50b? Yes. Minus 15 minus 5. So 50b minus 20. F of negative 5 would give me the same answer as that one. It would be 50b minus 20, because you would just plug in negative 5 to the bottom. 2bx squared plus 3x minus 5. So I'm not going to do it again because I already did it once. So here is my second equation. Right? So we did this actually last chapter. We have to solve for a and b. There are two linear equations. There's three ways to solve two linear equations. When you're trying to solve for two letters, two variables, you can use elimination like we did last chapter. Or this one you might be a little easier if you use substitution. Substitution means plug in. I know what a is, right? A is negative 20b. So just plug it in for a and solve it for b. You could do that. Or you can get a and b on the same side, set it equal like we did last chapter. Doesn't matter. Doesn't matter. Okay? So this one, since we did one already, since we've done a bunch in using elimination, I'm going to use substitution this time, just because I haven't showed that yet. So we know, according to this guy, that a is negative 20b plus 3. I also have an a over here. So I'm going to swap them. Substitution. Everywhere there's an a in the second equation, I'm going to swap in what it's equal to. What is it equal to? Negative 20b plus 3. So now in my equation, there's only b's. There's no a's in there now. Well, if there's only one letter, you can solve for it. If there's only one variable, you can solve for it. Okay? So I'm going to do that down here. Okay, so this is example 4 continued. Okay, so I have negative 5 times negative 20b plus 3 minus 6 equals 50b minus 20. So I distribute the negative 5 and then combine like terms. So you get 100b minus 15 minus 6 equals 50b minus 20. Combine like terms. I can combine these two guys to make negative 21. Okay. Get b's on the same side.
It just seems like an out of the ordinary answer.
So we get 50b minus 21 equals negative 20.
This is
Add 21 to both sides.
can't believe it. It's gonna be.
So you get 50, b equals 1. Divide by 50, you're going to get a very small answer. 1/50th. B is 1/50th.
All right, so
So now that you know B, we're going to use that to solve for A. So we're going to go back to our other two. Okay. So we're going to use one of these two guys. We're going to use either this guy or this guy here. I know what B is. I know B is 1/50th, right? So you can plug it in for B, either one of them, and solve for A. I'm going to use the left one since all I got to do is plug in, multiply, and add. The other one I would need to do some adding and subtracting and other stuff. So we get A equals -20 times B plus 3. We just found out that it's 1/50th. B is 1/50th. So you would get -20 over 50 plus 3. That's -2/5 plus 3. Well, 3 is 15/50ths.
5.
So we're going to get, what, 13 fifths?
Yep.
Done.
This sucks. Oh man.
Okay. We'll do one of those and then we'll be done. Yeah, so that last page,
Man.
there's like 3 or 4 questions. We'll do one of them and then we'll be done for today. Then you guys can start on your practice. Okay? Those, like I said, everything, this whole lesson is a FRQ question waiting to happen. There will more than likely be on the next test the test we take next week, at least one of your FRQs will come from this lesson. Will it be a solve for A or B? Maybe. Will it be a check for continuity, check for differentiability? Maybe. Something, those are very common. Usually you don't see these on multiple choice parts of the test. They're usually free response. Okay? All right. Let's take a look at, let's see. I'll make it easy on you guys. Let's do number 8.
What? Oh, okay.
The one after number
first
7.
one.
So do that
So
one.
the next is 1.
So on number 8, or also known as number 2, they're checking differentiability, just differentiability. So we don't have to worry about finding A or B. We don't have to worry about checking continuity. You can if you want, but you don't. It's not required. This one's just checking differentiability. So we need the derivative to check differentiability. So the derivative is going to be 2x when x is less than or equal to 1, or just 2 when x is greater than 1. So now I'm going to plug in 1 to the derivatives. So I get 2 times 1 equals 2. Yep. Both of those are equal. So yep, we're differentiable. That means there's no, it's going to be continuous. There's going to be no sharp turns. We're all good. Okay? So f of x, so we always want to answer the question. F of x is differentiable at x equals 1. And because it's differentiable, that means it has to be continuous. Okay? All right.